Welcome back, chemists. This is our second lecture video where we will look at matter and energy. So if you remember from our first lecture video, we defined chemistry as the study of matter, specifically where we look at the different composition, structure, properties, and reactions of matter. So how else can we classify matter? How can we categorize all the stuff that's around us in our world? So let's dive in. All right, so let's come up with a more scientific definition of matter. So I have an example here. I have a sentence and its corresponding chemical reaction. So both these things mean the same thing. So we react liquid ethanol. So see the L for liquid. This is ethanol. Reacts with oxygen gas. So plus O2 gas will produce. That's what the arrow means. Carbon dioxide gas and water vapor, so CO2 gas and H2O gas. So in this example, what constitutes matter? Well, let's get our more scientific definition of matter, because in the first set of lecture slides, we just defined matter as the stuff that makes up our world. I mean, that's true, but let's come up with a chemistry definition. So matter really is anything that has mass and occupies space, meaning that it has volume. It can be big or small, and it can be living or non-living. All right, but since we are chemists, we're mainly going to look at the non-living side. Go to biology for living matter, but we're going to look at non-living matter. So if you're ever confused about whether something can be considered matter or not, do the thought experiment. Can I put it in a jar? If you can put it in a jar, it's probably matter. So in our example here, the first substance is a liquid. I can put a liquid in a jar. I could just pour it on in, pour it in. So this first substance, which is ethanol, is matter because it's a liquid. So what about the other things, these three gases? Well, I can put gas in a jar. If I screw on the cap real tight, then the gas won't leave. So this O2, CO2, and H2O gases, all of those are examples of matter too. So now the question is, so we've defined those are matter, but can we define them and classify them any further? Can we differentiate them? So that brings us on to classifications of matter. There's only two umbrellas under matter. There's either pure substances or there's mixtures. You and I on a daily basis mainly interact with mixtures, unless you're in lab. In labs, you are more likely to come into contact with pure substances. All right, so let's just get these definitions out of the way. So a pure substance has to have uniform properties throughout. It cannot be separated physically and has a fixed or constant composition. So my example here usually is water. It has to be pure water. So I'm not talking about tap water. It has to be pure water. So there's my example. Only one substance has to be present, and like I said before, it's uncommon to come into contact with pure substances like pure water, the water that you and I get from like the tap or in a river that you see. There's other things in that water, even the water that you drink. There's minerals and there's dissolved oxygen and CO2 in that water. It's not actually pure. All right, so then our second classification of matter is mixture, which is much, much more common. Mixtures contains two or more substances that are not chemically combined and can have variable composition. Right. So my example here is going to be salt water. So what's important here is that you can physically separate it. Right? So those are the definitions. I think it might be easier to just kind of look at this map of types of matter. We'll go through this whole list. Right now we're at this first tier, right? So types of matter, like I said, you can only either have pure substances or mixtures. So here, pure substances, only one type of substance present, a definite composition, and cannot be separated by physical processes. So my example was H2O. H2O pure, sorry, I should put pure. Pure H2O has a definite composition. There's 2 hydrogens for every 1 oxygen. I can't separate this anymore. So if I start taking hydrogens and oxygens away, right, it would no longer be water anymore. All right. So I can't separate them physically. I would have to start using some type of like chemical process to start splitting it. All right. And only one type of substance. If I had a glass of pure water, all that you will see in there are H2Os. Then we have mixtures. So my example was salt water. So salt water contains, you guessed it, salt, NaCl, and water, H2O. There's 2 substances present. It can have, what I mean by variable composition is that I can have different ratios of salt and water, and it can still be considered salt water. You know, I could have 50% salt, 50% water. It's still salt water. You know, I could have 1% salt, the other 99% is water. It's still salt water. But the most important thing with mixtures is that it can be separated by physical processes. If I had salt water and just let all the water evaporate, I could eventually get all that salt, that solid salt back. And that's what differentiates a mixture and a pure substance, right? Because I cannot physically separate H2O using a physical process like evaporation or distillation or filtration. All right, so that is pure substances and mixtures. So now we'll go down another tier and more specifically look at what different types of pure substances are there and what types of mixtures are there. So within pure substances, there can only be 2 different types of things. Either an element or a compound can be a pure substance. So the first one that we'll look at is an element. So our definition for element is a substance that cannot be made from or decomposed into simpler substances by normal chemical means. So if you've heard of the term element before, what we mean is the elements on the periodic table. So this is a periodic table. I'm actually going to laminate these periodic tables for all of you and hand them out during our first recitation together. All right, so elements, we find these on the periodic table. So the elements on the periodic table, I have a couple examples, are copper. So Cu is copper, that's here on the periodic table. We have mercury and we have bromine. So all of these are elements. And so if we look back at our definition, elements cannot be made from or decomposed into simpler substances. So if we took one copper atom and we tried to split it even more, what we would have to do is actually start to remove or cut protons, electrons, and neutrons. And then once you have to, start removing protons, you actually change the element. So once we have one copper atom, you can't split it up anymore. So that is our definition of an element, a pure substance, because you can't split it up anymore. And so, I have some examples, copper, mercury, and bromine. So also, if we relate this back to our example on that second slide, the second slide of this slide deck, oxygen is also an element. Oops, right here. So our oxygen, in our example, this is an element, because you can find it on the periodic table. There are only oxygens within this substance right here. So O2 is actually how oxygen is found in nature as diatomic oxygen. So that's why it is O2. But yes, this is an element because there's only oxygens within it. So this brings us to our next type of pure substance, which is compound. So what we'll see here is that Our other three examples, other three substances in this example are actually compounds. And you can see, because there are actually different elements within these compounds, that's why we consider it a compound. So there's element. The other type of pure substance is, in fact, a compound. So the definition that we have there is a substance that can be broken down into two or more simpler pure substances by chemical means. So remember what our definition, or what types of pure substances there are. You can either have an element or a compound. So if you can take a compound and break it up into smaller, simpler compounds, that first original thing is a compound. If you can take a compound and split it up into elements, that's your original thing is also a compound. A compound has a fixed proportion and a distinct structure. So what I mean by that, so maybe it'd be better to show an example. So salt here. Salt has the chemical formula Na, or sodium chloride. So what this chemical formula is telling us is that there's one sodium for every one chloride. So regardless of the size of the sample, the ratio between sodium and chloride will always be 1 to 1. That's what we mean by a fixed proportion. Sugar, the same thing. So if we have a sugar sample, a really large sugar sample, like let's say we have like a 5-pound bag of sugar, there will always be 12 carbons for every 22 hydrogens for every 11 oxygens. That's what we mean by a fixed proportion. What we mean by distinct structure is that regardless of where you find the compound, it will always look the same. So here in this photo, I have, this is a picture of water, which we have has a formula of H2O. H2O, water, has a fixed proportion. There are 2 hydrogens for every 1 oxygen. So you see, this is the structure of water. This big red ball is oxygen, and then there's 2 hydrogens right here on the structure. So wherever you find water, if you had a microscope that could look at the atoms, of the molecule, you would always see that water has this type of structure, regardless of where you find it. And then some other examples of compounds. If we go back to our example from the top, ethanol, water, and carbon dioxide from our example are also compounds. So if we take a look at that, so in this example, ethanol is a compound because there are, carbons, hydrogens, and oxygens. We could split ethanol into simpler elements, carbons, hydrogens, oxygens, right? CO2, or carbon dioxide, this is also a compound because you can split it up into carbons and oxygens, which are elements. They're also pure substances. And then water, lastly, is also a compound because you have hydrogens and oxygens. While, remember, our oxygen here in this chemical equation, only oxygen, our diatomic oxygen, is an element because there's only one type of element there. You cannot split it up any further without actually changing, like removing protons and electrons. How do we differentiate elements and compounds? Well, compounds are made of elements from the periodic table, different elements of the periodic table. So I have here an example, table salt, or sodium chloride. We've been talking about this whole lecture. Sodium chloride is made up of 1 sodium atom for every 1 chlorine atom. And then together, when they are combined, produce sodium chloride, or the salt you and I know. So the proportion is 1 to 1. But how is the compound different than the elements themselves? So sodium chloride, we can, we ingest on a regular basis. That's table salt. But just a sodium atom is actually really explosive if you just had a sodium atom. Chlorine exists as a gas, actually, as Cl2, chlorine gas. So separately, those elements are actually, pretty dangerous. But when combined together in a compound are, is just as benign as table salt that we put on our food every day. Um, so the reaction actually, where the elemental forms of sodium and the elemental form of chlorine, when it combines, actually produces this really cool reaction, which I will show you right now in this video.
I took the sodium back out and I heated it a lot until it was molten red. This time, when I placed it back into the chlorine, it was a much more spectacular reaction. The sodium burned really bright and it turned my Erlenmeyer flask into a lantern. From demonstrations and other resources that I've seen online, I honestly expected this reaction to last no more than a few seconds. I'm not sure if I just used more sodium than the other demonstrations, but the reaction seemed to go very vigorously and bright for at least a minute.
So the reaction that you just saw is this one that I have the chemical reaction for right here. That scientist took a sodium solid, which was in a test tube, elemental sodium, and he combined that with chlorine gas, which was in the Erlenmeyer flask. And then when he heated the sodium up, what he saw was this bright light that shone from the Erlenmeyer flask. And actually, at the end of the reaction, what he saw left in the test tube was solid sodium chloride, which is white. So I'll show you the picture of that right now.
The test tube was coated in a thick layer of nice white sodium chloride. I tried to scratch off as much as I could, but it's honestly very hard and stuck very tightly to the glass. When it's poured out, you can see that this product is much cleaner than the last run.
So the white substance that you saw at the end of that video is actually the compound sodium chloride, which was white. So sodium chloride is a compound, while the starting materials that the scientists used were the elemental forms of sodium and chlorine, which are elements from the periodic table. So moving on to our next type of matter, which is a mixture. A mixture contains two or more substances that are physically combined and can have a variable composition. Our example earlier that I used was salt water. Salt water contains salt, or sodium chloride, and water, which is H2O. They are not chemically combined. We mix them together to make a mixture, and you can physically separate it. So some examples of physical separation techniques includes filtration, evaporation, and distillation. So if we wanted to separate salt water, we could physically separate it through evaporation, where we evaporate the water off and leave the solid sodium chloride behind. And like I said before, we can have a variable composition of salt water, meaning that the components can be in different proportions. We could have a 50-50 mix of sodium chloride and water. We could have 1% of sodium chloride in water. It doesn't matter what the mixture percentages are, it will still be salt water. So that's what we mean by variable composition. Salt water mixture can be made with missing an H, with different concentrations. Okay, so within mixtures, there's two different types of mixtures. Our first type is a homogeneous mixture, where there is one visible phase, or it's uniform. It has a uniform composition and properties throughout. So our saltwater example would be an example of a homogeneous mixture, because as long as we dissolve all of the salt in the water and we have just one saltwater solution, that would be homogeneous. As long as it looks clear throughout, that would be a homogeneous mixture. So this is also called a solution. Solutions can be separated through methods, physical methods such as evaporation or distillation. You cannot filter a homogeneous mixture because it's uniform throughout. It's all one phase. So in our saltwater example, it's all a liquid. So if you filter our saltwater solution, all of it should just go straight through the filter paper. So in order to separate a saltwater solution, you would need to use our evaporation technique. So other examples of homogeneous mixtures includes a copper sulfate solution. So in this picture, you see that it's a uniform blue color, right? So it's all a liquid, it's all one phase. Other types of homogeneous mixtures in the gaseous phase would include air. The air that we breathe contains a lot of different compounds and elements, such as like diatomic oxygen, diatomic nitrogen, xenon, CO2. And so all of those compounds exist in one phase in the gas phase, and it's absolutely uniform throughout. That's the air we breathe. So that would be a gas phase homogeneous mixture. This copper sulfate solution is a liquid phase example of a homogeneous mixture, while this other example, brass, is actually a solid example of a homogeneous mixture, where brass is composed of copper and zinc, and they're uniform throughout. All those atoms of copper atoms and zinc atoms are uniform throughout, but in the solid phase. Our next type of mixture is a heterogeneous mixture. So if you remember from the homogeneous mixture, it's uniform throughout. So a heterogeneous mixture is actually not uniform throughout. So in a heterogeneous mixture, you see visibly different phases in the mixture, and each phase has different properties. So heterogeneous mixtures are not uniform throughout. It has a non-uniform composition. Its composition can vary, and you can easily manually separate heterogeneous mixtures through things like filtration. Or, I mean, if the pieces are large enough, you could just pick them out with like tweezers or your fingers or something. So some examples of heterogeneous mixtures that I have here are things like oil and water. So if you've ever tried to mix oil and water together, you see that there are different phases that oil and water do not mix. So there are different phases present, and oil has different properties than water. So that would be an example of a heterogeneous mixture. Something like muddy water. You have water and like solid mud in one mixture. That would be another example of a heterogeneous mixture. If you left muddy water out long enough, you would eventually see, the mud layer sink to the bottom while the water stays on top. And if you shake it again, you could let them separate over time. Something like a salad that has like lettuce, carrots, cucumbers, something like that. That would be another example of a heterogeneous mixture, because there are visible different solid phases. You can pick the cucumbers out. You can pick the carrots out, or something. Something like salad dressing. If you see salad dressing on the store shelves, you can see visible like herbs and spices on the bottom layer of the salad dressing, and then like an oil layer on top. Or something like a pizza. A pizza is also a heterogeneous mixture because you can pick toppings off. If you have a pineapple and ham pizza, I know that's controversial, but you can pick the pineapples out if you wish. That would be a heterogeneous mixture because you can manually separate those toppings off easily. The point I want to drive home with heterogeneous mixtures is that you can easily manually separate them. So I have an example here with a mixture of some iron filings and like some sand or something. You can use a magnet to easily remove those iron filings if you so wish, and remove them from the sand mixture, like I have there. Right? You can easily do this at home. I'm going to do it right now. So I have a container here. It's not sand, but it's like some paper shavings, and then in this hand I have some magnetic or some metal nuts. Right, I just pulled from my garage. All right, so I'm gonna mix them. I'm gonna mix the paper shavings and the metal nuts together. So I could go through and stick my hand in and pick out the nuts one by one. Right, that would be an easy way to manually separate them, but that's not fun. So I'm going to use this really strong magnet. This is a neodymium magnet. I actually use it for magnet fishing. I've never caught anything interesting, just like rusty nails. So I can remove those nuts that I put in this mixture in here, right? Whoop, there it is. So I can easily remove those nuts, and see now they're just like right there on the magnet on the side of the container. So I can easily remove them through manual means, manual separation, right? And now they're on the magnet. All right, so I have separated paper shavings from metal nuts. So this chart really summarizes the thought process that you might go through to determine, is something a pure substance? Is it a mixture? All right, so if I ever give you an example piece of matter, the first question you should ask yourself is that sample, is that piece of matter uniform throughout? You know, if you can clearly see specks of stuff in it, then that's not uniform. But let's say it is uniform. Let's say, I give the example sugar water. Right, I gave you a sample of sugar water. Sugar water, it looks like water, right? It's uniform throughout, it's colorless throughout. So we would say, yes, it's uniform, it's homogeneous. But we need to go a little bit further. We need to think about, are there different substances present? Sugar water contains sugar and water. So yes, there are two substances present. So with our example of sugar water, that would be a homogeneous mixture. So sugar water. Let's take a step back. So sugar water is a homogeneous mixture because it's uniform throughout. It contains sugar and it contains water. Let's say you go to the store and you buy nail polish remover, pure acetone. Acetone contains carbons, hydrogens, and oxygen. So if you go to the store and buy pure acetone, it's colorless. It looks like water. Right? So it would be, acetone would be homogeneous. But now you need to ask yourself, so we've gone through this part of our diagram. You need to ask yourself, are there two or more different substances present? So if I told you that acetone contains carbons, hydrogens, and oxygens all chemically combined, so no, there aren't any other substances. Pure acetone only contains acetone. So we're going to say no, that this is a pure substance. Acetone is a pure substance in one physical state, which is a liquid. When you buy acetone, it's a liquid. All right? So we have a pure substance. But within pure substances, there's two different kinds. There's an element, or if it's a compound. So, I can just think off the bat, is acetone on the periodic table? No, it's not. Acetone contains carbons, hydrogens, and oxygens that are all chemically combined. So because there's different elements chemically combined in acetone that you buy at the store would be considered a compound. All right. So if we go back one step further, or one step, so let's say you have a pure substance, right, and it can't be broken down into simpler substances. Let's say I had pure gold, right? Gold. If I had a chunk of 24 karat gold, it's uniform throughout, so gold would be homogeneous. Are there two or more different substances present? No, it's just gold. It's pure gold. So no, gold is a pure substance in one physical state. In this state, it's the solid state, right? And now we can ask ourselves, can this pure substance, gold, be broken down into simpler substances? So gold is an element on the periodic table. So no, it can't be broken down into simpler substances. We'd have to start removing electrons and protons and stuff. So gold, pure gold, would be an element. So let's go back to the top of our chart here and ask ourselves, is a piece of matter uniform throughout? Let's say no, it's not uniform, that you can see specks of things. So let's just say like salad dressing, Italian salad dressing. There's lots of like herbs at the bottom. All right. So I have a sample of salad dressing. It is not uniform throughout because I can see herbs and spices at the bottom. So no, it's not uniform. This is a heterogeneous sample. Now you should ask yourself, are there different substances present? Well, yeah, in salad dressing, there's herbs, there's like water, there's vinegar, there's oil. So there's different substances. So salad dressing would be in fact a heterogeneous mixture. Okay, so this is where it kind of gets tricky. Are there two different substances present? So if we take a step back, I'll give you an example of something. Let's say we have ice water. You have a tall glass of water with ice cubes in it. So if we go back to the top of our chart, does this sample, our ice water, Does that sample have the same properties throughout? No, it doesn't. There's solid ice cubes and then there's liquid water. So it is not uniform. So therefore it would be heterogeneous. So now you need to ask yourself, are there two or more different substances present? So in this case, ice is just, water, H2O. Water is also H2O. They're just in different phases. So ice is a solid, water is a liquid. So if I say, no, there aren't two substances present, no, it's technically still a pure substance. It's just there's two or more physical states, meaning in this case, a solid and a liquid present at the same time. Right? So ice water would be an example of a pure substance in just two different phases at the same time. I mean, you could still have just like regular water in one phase. That's still a compound. But in this case, it's just heterogeneous because there's two different phases present. So now if we go down the list, can the pure substance be broken down to simpler substances? So yes, water is H2O. There's hydrogens and oxygens. So ice water would in fact be a compound because water is H2O. All right, so that's how that chart works. You might go about trying to figure out whether things are mixtures or pure substances differently, but this kind of summarizes how you would go about that. So let's just do a learning check and make sure that everyone's following along. So in this learning check, so identify each of the following as either a pure substance or a mixture. If it's a mixture, identify as homogeneous or heterogeneous. So let's go through all of this. So I'm going to say Jif, smooth, peanut butter. See, I have to say Jif because, like natural peanut butter that you get sometimes at the store, they separate. So then this question wouldn't make sense. So I'm going to say Jif, smooth, peanut butter. So with smooth peanut butter, I would say, the first scoop is the same as the last scoop. So it is uniform throughout. But now you need to ask yourself, is there two or more different substances involved? Well, yeah, peanut butter contains a lot of different things. You just look at the ingredients list. It contains peanuts, it contains oil, there's protein, there are carbohydrates, there's probably water. So I would say smooth peanut butter is a mixture because it contains a lot of things, and it's homogeneous because your first scoop is the same as the last scoop. You can't really separate smooth peanut butter. Homogeneous mixture. So on the flip side of things, what if I said, okay, what about chunky peanut butter? Chunky peanut butter has chunks of solid peanuts in it. So the question is it uniform throughout? No, it's not because there are chunks of solid peanuts in it. So this would be a heterogeneous mixture, right? So our next example is aluminum foil. Aluminum foil, I would say, is it uniform throughout? Yeah, the first, strip of aluminum foil that I tear off is the same as the last strip. So yes, it is homogeneous. But now you need to ask yourself, are there more than one substance present? Well, no. Aluminum foil is just made of aluminum. All right, so there's only one substance present. So that would make aluminum foil a pure substance because aluminum is the only thing present in it. Now we can ask ourselves, past pure substance, is it an element or is it a compound? Well, aluminum, you can see it on the periodic table, so it would be an element. Aluminum is Al on the periodic table. All right. So now the example is methane. Methane is the compound CH4. All right. Methane is a gas also. So a gas is uniform throughout. If we have methane gas, it's uniform. So now we need to ask ourselves, is there more than one substance present? Well, no, methane is just CH4. This is chemically combined. So methane is a pure substance. Now, can it be broken down into simpler elements? Well, yeah, there's carbons and hydrogens present. So instead of an element, this methane pure substance is actually a compound. So that's different than aluminum foil. excuse me, both aluminum foil and methane are pure substances, but aluminum foil is an element because it's seen on the periodic table, while methane, because it has the formula CH4, is a compound because it can be broken down into carbons and hydrogens. All right, now another example, air. Air, the air we breathe is made up of lots of different things. Oxygen in the gas form, oxygen, nitrogen, xenon, CO2, all of those things. All right. But again, if we go back to our chart, is air uniform throughout? Well, yeah. Air that I breathe in this room or that I breathe in my kitchen, it's the same pretty much. So, yes, air is uniform throughout. But now ask yourselves, are there more than one substance present? Well, yes, I just told you. Air contains all these things, oxygen, nitrogen, xenon, carbon dioxide. So because more than one substance is present in this uniform sample, this would make this homogeneous. Homogeneous mixture because more than one substance is present in this sample. All right, now finally, ice. Ice is just solid water, H2O. All right, ice is pretty uniform throughout. All right. Now you need to ask yourselves, is there more than one substance present in an ice sample? No, because ice is just composed of H2O, and that's it. All right, and the hydrogens are chemically combined, so this would make this a compound and a pure substance. It would make it a compound because we can separate it into hydrogens and oxygens.